Hello. In this last video of our group theory course, we are going to see how group actions can help us to study groups that have order of the form p to the n, where p is a prime number and n is a positive integer. Let's recall some of the basic properties of group actions. When we have a group G and a non-empty set S, we say G acts on X via the map or via the action star if star is a function from G cross X to X. I feed it a pair of elements, one inside the group, the other one inside the set, and this pair is sent to G star X. Intuitively, we are thinking about G acting via symmetries on the set X. So if this function has the following properties, if I start with a neutral element, it's supposed to behave like the identity function from X to X. And if I give it G1 and G2, then the way that they act on X is compatible with group operation inside the group G. That means G2 star X. And then if I apply G1 on this point, it's the same as applying product of G1 and G2 to the initial point X. If a star has these properties, we say that G acts on X via star. And we say Y is G similar to X. So again, think about it like this, that G is certain symmetries of the object X, and I am asking myself, what other points inside the set X look like the small element, the small point X, if I only consider symmetries that come from the group G. Then we denoted this by this relation. We say X is G similar to Y, or we say Y is G similar to X, or we say X is related to Y in this sense. We prove that this relation is an equivalent relation and motivated by correspondence between equivalent relations and partitions. We looked at the equivalent class of the point X, and we saw that this is nothing but all the points that are similar to X, G similar to X. That means all these points that we can reach from X using symmetries within the group G. So that's the residue, and that's the equivalent class of the point X, and therefore these equivalent classes form a partition. We call this set to be the G orbit of X, and denote this by capital G, the group G, acting on the point X. So that we call the G orbit, and so therefore the G orbit of X is nothing but the equivalence of X with respect to this relation. And because equivalent classes form a partition of the given set, we deduce that the set of all the orbits form a partition of the set X. And moreover, two orbits, orbit of X is the same as orbit of Y, precisely when the equivalent class of X is the same as the equivalent class of Y, and that one happens precisely when X is in relation to Y, and that means that Y is G similar to X. Now, if we denote the set of all G orbits by X modeled by G, factored out by G, the quotient space, if we denote it by this, then we know that as I vary among the G orbits and I add cardinality of these G orbits, because they form a partition of the set X, I end up getting cardinality of the set X. Of course, when X is finite, otherwise it doesn't make sense to add these infinite numbers. So if X is finite, then I'm giving you a finite partition if I add cardinality of each one of the elements in in this partition, I end up getting cardinality of the set X itself. This equation, though we reached to it very naively and rather easily, is extremely crucial. You have already seen an important implication of this equation when we considered an action of a subgroup on the ambient group G by left multiplications and end up getting the Lagrange's theorem using this result. So you have already seen implications of this equation. In this video, we see further applications of this equation. So if I want to use this equation as we did it in the case of Lagrange's theorem, I need to understand cardinality of a single orbit. I need to have a better understanding of orbits in general in order to be able to use this equation. And it's not surprising that in order to understand cardinality of this set, I need to understand how many of these symmetries do not move X at all. So some of the symmetries move it, and I get new points in the G orbit. I get new points that are G similar to the point X, but some of them do not move them at all. And then therefore I do not get new points inside the space. So it is not surprising that we have to understand those symmetries that come from the group G that do not move X, that fix X, that stabilize X. We say these elements of this group stabilize the point X, and we put them together in a set, and that set is denoted by G sub X. So G sub X consists of all those elements of the group capital G that stabilize the point X, that do not move the point X, that fix the point X. So we use all these phrases in order to say that G star X is X. If I consider this subset of the group G, it turns out that this subset is indeed a subgroup. And we call this subgroup the stabilizer subgroup of G with respect to the point X. So this subgroup is called the stabilizer subgroup of G with respect to the point X. Okay, let's see why this is a subgroup. Again, we are going to use the subgroup criterion in order to show that this is a subgroup. And that means, first I need to argue why this is not empty. And as usual, in order to show that this is not empty, we are going to prove that the neutral element belongs to this set. So I want to show that neutral element belongs to this set. That means I have to apply this to the point X, and then I have to say that it is equal to X. But this is the case, because we are saying that the star is an action, and by definition, the first property of group actions, the neutral element is not supposed to move any point. It's supposed to act like the identity function. So the neutral element acting on X gives us X, and that means it belongs to the stabilizer subgroup of G with respect to the point X. It belongs to G sub X. Next, I want to show that if G1 and G2 are two elements of the stabilizer subgroup of G with respect to X, then so is G1 times G2 inverse. So this implication is what I want to show in the next step. If I show this implication together with the fact that this is not an empty set, we deduce that G sub X is a subgroup of G using the subgroup criterion. Okay, let's start with the hypothesis. Knowing that G1 and G2 belong to G sub X means neither of them move X. That means G sub 2 star X is X, and the same is true for G sub 1 star X. But we'll come back to G sub 1 later. As you can see here, I need to get some information about G2 inverse, and that's why I'm going to let G sub 2 inverse act on both sides of this equation. By letting act on this side, I get G sub 2 inverse star of G2 star X is the same, and on this side I get G sub 2 inverse star X. Using the fact that the action is compatible with group operation, I can drop one of these stars, put the parentheses around G2 inverse and G2, and that way I end up getting the neutral element of the group G. So this is the neutral element of the group G, and we know neutral element fixes the point X. So this is altogether simply X. And on the other side, I get G2 inverse X. Again, this part is the neutral element star X is X. So we get that G2 inverse also fixes the point X. So it belongs to the G sub X. But this is not what I'm interested in. I want to show that G1, G2 inverse fixes the point X. So I start with this equation, apply G1 to both sides. Let G1 act on both sides of this equation. So on this side I get G1 star X, and the other side I get G1 star this point. Again, I'm going to use the fact that action is compatible with group operation. So this side is simply G1 times G2 inverse acting on the point X. How about this side? This side is simply X, because G1 is in the stabilizer subgroup of G with respect to the point X. So G1 star X is equal to X. So this side is X, and the other side is G1, G2 inverse star X. Altogether, we deduce that X is equal to, instead of this, I write this, G1, G2 inverse star X. And that means this element of the group stabilizes the point X, so it does belong to the stabilizer subgroup of G with respect to X. And that completes proof of this lemma. So the stabilizer subgroup of the group G with respect to the point X is indeed a subgroup. Next, we are going to show the so-called orbit stabilizer theorem, which gives us a very good idea, pretty good understanding of orbits. So what is the orbit stabilizer theorem? Suppose that I give you a group and an action of this group on a set X. And suppose the action is given by star. Then for every point X, the following is a bijection between the left coset of the stabilizer subgroup of G with respect to X and the points in the G orbit of X. What is the function? I feed it a left coset of the stabilizer subgroup with respect to X, and it gives me the point in the G orbit after this coset representative G acts on the point X. The claim is that this function is a bijection. In particular, if I'm dealing with finite sets, cardinality of this is the same as cardinality of that. And remember, cardinality of the quotient of G by a subgroup is simply the index of the subgroup. So that means the index of the stabilizer subgroup with respect to X is equal to the cardinality of the G orbit of X. So this way, I get a control, I get an understanding of the cardinality of the G orbits of X. In particular, we deduce, combining it by Lagrange's theorem, we deduce that cardinality of every orbit divides cardinality of G. Remember, index of subgroups divide cardinality of the group. So from here, I can deduce that cardinality of every G orbit divides cardinality of the group G, which is a non-trivial statement. In fact, Lagrange was interested in this statement, and that's why he proved his result. He was studying zeros of polynomials, and along the way, he was trying to understand symmetries of zeros of a given polynomial, and he was interested in showing that an orbit of a solution under symmetries of that polynomial actually divides the degree of that polynomial. so to speak. So you might study this if you study field theory. In any case, so this is the orbital stabilizer theorem that we want to show. As you can see, this function f a priori depends on the choice of a coset representative, and we need to argue that it is indeed independent of the choice of this g. So if I change this g to some other representative of this coset, why do I end up getting the same point in the g orbit of x? That's the question that we have to address. Okay, so what is the precise implication that we have to address? Assuming that the coset given by G1 is the same as the coset given by G2, we need to prove that the action of G2 on X gives me the same point as action of G1 on X. So I'm going to get the same point on the G orbit of X using both G1 or G2. So this is the implication that we need to show. Let's go through the argument. Knowing that these two coset representatives, these two cosets are equal, so G1 and G2 are coset representatives of the same coset, or representatives of the same coset, we deduce that G1 inverse times G2 belongs to the subgroup. That's a general rule for left cosets, that the coset represented by G1 is equal to the coset represented by G2 precisely when G1 inverse G2 belongs to the given subgroup. So G1 inverse G2 is inside the stabilizer subgroup of G with respect to X. That means what? That means as I apply this element to the point X, I'm not moving it. Now let's multiply both sides by G1. That means I'm letting G1 act on both sides of this equation. I get that G1 acting on this point is the same as G1 acting on this point, this one acting on X. Using the fact that this is an action, star is compatible with multiplication inside the group, I can remove the star and reorder the parentheses. I end up getting this. And remember again, multiplication in the group is associative, so I can cancel these two. I end up getting just G sub 2 on the left-hand side. So this, on the left-hand side, I have G sub 2 acting on X, and in the right-hand side, I get G1 acting on X, and that's exactly the equality we were looking for. So it is indeed a well-defined function. Next, I'm going to argue why it is injective. I want to show that f is a bijection. So we have already discussed that it is a function. Next, I'm going to show why it is injective. And finally, I will discuss why it is surjective. From all these parts together, we deduce that f is a bijection. Okay, what does it mean that f is injective? What kind of implication do we need to show? We have to show that if f of a coset is equal to f of another coset, then in fact they are the same cosets. So this is the implication that we need to show. So that means that f is injective. Okay, now let's start going through these steps. F of this coset is simply G1 acting on the point X. And f of the other coset is G2 acting on the point X. So as I let G1 and G2 act on the point X, I end up getting the same points. Now I want to have only X in one of the sides. I let G1 inverse act on both sides of these equations. So I get that G1 inverse acting on this point is the same as G1 inverse acting on this point. Using the fact that star is compatible with operation in the group G, I can reorder the parentheses, remove the star on both sides. I get G1 inverse G1 star X is the same as G1 inverse G2 star X. But remember, G1 inverse G1 is the neutral element of the group, and neutral element of the group star X is always X no matter what X is. So on the left-hand side, we end up getting X, And in the right-hand side, I get G1 inverse G2 star X. That means this element is in the stabilizer subgroup of G with respect to X. And we have discussed this, that G1 inverse G2 belongs to a subgroup precisely when the left coset with respect to represented by G1 is the same as the left coset represented by G2. So I get this equality, and that's exactly what we wanted to show. So F is in fact injective. And finally, let's see why F is surjective. This one is rather easy. Essentially, that's just the definition of the codomain. Remember, the codomain of F is the G orbit of X, and every point in the G orbit means a point of this type, G star X for some element G. But this is simply F of the coset represented by G. So this means every element of the codomain is in the image of F. It's F of something. And that means F is surjective. So F is a well-defined function. It is injective and surjective, and therefore it's a bijection. In particular, if the codomain and domain are, if one of them is finite, the other one is finite, and they have the same cardinality. And so the index of the stabilizer subgroup of G with respect to X is equal to the cardinality of the orbit of the point X. Okay. Now let's see how this can help us to get a better understanding of finite groups of order p to the n. So the next theorem is fundamental in understanding, so maybe basic understanding of finite groups of order p to the n, especially when we want to understand them as subgroups of certain finite group. At the surface, you might not see the importance of this theorem, but immediately afterwards, we are going to show two results. One of them, Cauchy's theorem, and the next one, the so-called Silow's first theorem. And both of them are important results in finite group theory. And you see how this theorem that we are going to discuss is instrumental in proving those results. Okay, so what is the statement? The assumption is that I'm giving you a group whose cardinality is of the form p to the n, where p is a prime number and n is a positive integer. And I give you an action of this group on some finite set X. So X is a finite set, which is not empty, and P acts on this set via star. We are going to denote by X sub P the set of fixed points of P. That means all the points of X that are stabilized by every single point inside the group capital P. So for every G inside capital P, G star X is supposed to be simply X. So they are fixed by all the points of by all the elements of the group P. So this set is denoted by X sub P, and it's called the set of fixed points of P. Now, this theorem says that cardinality of X is congruent to the cardinality of the number of fixed points of X, fixed points of P mod the prime number P. Okay, so let's see how the proof goes. We have already discussed the connection between cardinality of X and action of P. Namely, we know that P orbits form a partition of the set X, and therefore cardinality of the set X is equal to the cardinality of distinct P orbits. So if I take all the different P orbits and I add their cardinalities, I end up getting cardinality of the set X. By the orbit stabilizer theorem, I know this orbit has, the number of elements of this orbit is precisely the index of the stabilizer subgroup of P with respect to X. So the P orbit of X, the cardinality of P orbit of X is exactly the index of the stabilizer subgroup of P with respect to X, in P. We also notice that a point is in the fixed points of P precisely when its P orbit has only one point, and that is X, because every element of the P that I act on X, it's supposed to send it to itself. So the P orbit of X has only one point in it, and that is X. And that's equivalent to saying that all the elements of P are stabilizing the point X, and therefore the stabilizer subgroup of P, a stabilizer subgroup of P with respect to X is the entire P. So all these statements are equivalent. X is in the fixed points, the P orbit of X has only one point, the stabilizer subgroup of P with respect to X is the entire P. So that means what? That means if I look at all the orbits, I can separate them in two cases. Either this orbit has only one element, or it has more than one element. If it has only one element, then that one is giving me a point inside the fixed points, and vice versa. If it's in the fixed points, then it gives me a point, one orbit that has only one element. So that means if I rewrite this summation and split it into two summations, those terms that have more than one element, and I write it like this in this first sum, or those terms that have precisely one element. And that means instead of writing this, I need to write simply one, because there is only one element inside this type of orbits. And notice this summation gives me precisely the number of P orbits that have cardinality 1, because each one of them contributes 1 to this summation. So this summation tells me how many of the orbits have cardinality 1. Equivalently, I can say how many of these orbits have cardinality 1 is the same as saying that how many fixed points do we have. So the second summation is simply cardinality of the fixed points of P. So let's again stare at this equation. It is an important equation. We end up writing cardinality of X as summation of bunch of indices that are not 1 for sure. So some indices, index of some subgroups, and this index is not supposed to be 1, plus cardinality of the number of cardinality of the fixed points of P. Okay, now how can this help us to get this? Notice that this is a divisor of cardinality of P because of Lagrange's theorem. This divides cardinality of P. Now, cardinality of P is P to the n. So this means that these terms are divisors of P to the n. Now, divisors of P to the n are essentially P to the m for some smaller, for some integer that's non-negative and at most n. But we did not prove this result, but what we proved is that a divisor of P to the n is definitely a multiple of P unless it is 1. So every divisor of P to the n is a multiple of P unless it is 1. Now, these are divisors that are not 1 because P sub x is not supposed to be the entire P. Its index is definitely at least 2. So this is a divisor of P to the n which is not 1, and therefore it's a multiple of P. So all these terms are multiples of P. So that's it. So cardinality of X minus cardinality of the number of fixed points, cardinality of fixed points of P is a multiple of P, prime number P. And that completes the proof of this claim. But let me write down some of the details again and go through the written notes. So again, by Lagrange's theorem, we know cardinality of P is a multiple of the index. So this divides P to the n. Earlier we showed that if I give you a prime number P, every divisor of p to the n is either 1 or a multiple of p. Again, it's easy to show that all the divisors are of this form. We can use this fact that every divisor is a multiple of p and show that all the positive divisors of p to the n are in this set. We can show this by induction. But whatever method, the point is that this index, if it's not 1, it's a multiple of p. Now, if p sub x is not p, this index is not 1, and therefore mod p is 0. So this means that all the terms in the first summation that we had earlier, cardinality of x is equal to this summation consisting of the index of the stabilizer subgroups of those points where the stabilizer with respect to those points where the stabilizer subgroup is not the entire p. All these terms are multiples of the prime number p, and the rest gives us cardinality of fixed points of p. So these terms mod p are 0, so we get only this term, and that completes proof of this theorem. Okay, now let's see how this theorem can help us. We are going to use this theorem to prove Cauchy's theorem. What is Cauchy's theorem about? Lagrange's theorem says that order of any element should divide cardinality of the group. The converse of this statement is, of course, false, because if I give you a group of order n, it does not necessarily have an element of order n. In fact, it has an element of order n precisely when it's a cyclic group. But what Cauchy's theorem says is that if I start with a prime factor of cardinality of the group, then for sure there is an element of order p. So that's Cauchy's theorem, and that is what we are going to show. Suppose G is a finite group, and assume that P is a prime factor of cardinality of G, of order of G, then I can find some element of this group whose order is precisely P. So it is a partial converse of Lagrange's theorem. The proof that I'm going to present is a beautiful proof, and the idea is as follows, that okay, so when I say I'm looking for an element of order P, I'm telling you that I'm looking for a solution of the equation x to the p equal to the neutral element, but a non-trivial solution. Of course, the neutral element is a solution of this, but I'm looking for some solution that's not the neutral element. So I'm looking for a non-trivial solution of this equation. Now, the beautiful idea is to relax this equality, get a more relaxed version, and gain more symmetries, and then try to use these symmetries in order to find and then relate this equation that we have with some section of the new equation. So we want to find a more relaxed equation which has a lot of symmetries and try to use those symmetries in our advantage. In this example, the more relaxed version, so often that means that we are going to have more variables, and the more variables that we have here, instead of having a single variable x, I'm going to replace it with p variables. I'll have x sub 0, x sub 1, x sub 2, till x sub p minus 1, and the assumption is that their product is supposed to be the neutral element of the group G. So this new equation, we are asking what are the solutions of this equation, and then we look at a section of this. What is section? So we are interested in x to the p equal to the neutral element. If I look at those solutions for this equation, where x sub 0 is the same as x sub 1, and that is the same as x sub 2, and so on, till we reach to x sub p minus 1, and all of them are x. If all of these x sub i's are the same as x, then we end up getting a solution for the desired equation. This type of idea is actually used in for other questions in number theory as well. This is a beautiful idea. Whenever it works, one can get joy out of it. Another example that comes to mind is a beautiful proof by Heath-Browns of the following theorem of Fermat, and I encourage you to search for this proof of Heath-Browns and enjoy the details of the argument. But the general question is the following. The general statement that Fermat proof is the following: that suppose P is a prime number and mod for it's 1, like 5, like 13. In that case, you can find two integers, x and y, and write P as sum of squares of these two integers. So we want to see why this is the case. Again, the idea is, instead of solving this equation, I'm going to deal with a more relaxed version, but gain symmetries. The more relaxed version is solving this equation, x squared plus 4yz, and then trying to find a solution where y equals to z. If I find such a solution that y equals to z, then this would be a perfect square as well. So I would be able to write P as sum of two perfect squares. So this equation geometrically can be viewed like this: that I have P 1 by 1 blocks, and I can make this kind of fan shape out of them. I can put a square in the middle and then attach these handles to this square, where the square in the middle has x squared blocks, and each one of the handles has yz number of blocks. And the beautiful symmetries between these solutions is playing with the shape of these fans. So you start with this solution, and then you get another solution using continuing these lines. Then I end up getting this fan shape. Essentially, it is again a fan shape, but a different square is now used, and different y and z will be used. So starting with one solution, we can end up getting another solution, and the shape doesn't change if the yz itself is a square. So in that case, we end up getting so we are getting symmetries of the set of solutions, and the fixed points of that symmetries is going to give us the desired solution for this equation. So I encourage you to look for Heath-Browns proof of Fermat's theorem. In fact, there are also some videos in YouTube for this question. It's a beautiful proof, but it's the same concept. I'm giving you some equation, I'd like to solve it. That's hard. I'm going to relax it, gain more symmetries, and try to see if the fixed points of the symmetries give me the desired solution. Okay, let's go through the proof of Cauchy's theorem. So as I've indicated, I'm going to look at the equation x sub 0 times x sub 1 dot x sub p minus 1 equals to the neutral element. So I'm looking at all the p tuples of elements coming from the group G, cross G, so it comes from this group. All the components are coming from G, and I'm asking for those p tuples where their product is the neutral element. I put all the solutions in a set capital X. Notice that if I fix the first p minus 1 entries, then I can always fill out the last component in order to get a point inside the set X by simply letting it being inverse of product of the first p minus 1 entries. So that means the set X is nothing but these p tuples. The first p minus 1 can be anything you want, but the last one needs to be inverse of the product of the first p minus 1 entries. So altogether from this argument, we deduce that cardinality of x is nothing but cardinality of g raised to power p minus 1, because for the first component, I have cardinality of g options. For the second one, I have cardinality of g options, and so on till the p minus 1 component. Till there, I have cardinality of g options. But the last one then is going to be forced. So altogether, cardinality of x is cardinality of g raised to power p minus 1. Now, the magic happens right here. Here is the place that we are looking for symmetries. When I give you an equation, when I give you p elements of the group, and I tell you that their product is the neutral element, I can cut it in jth place. So I can take the first j terms and then put a parenthesis around it and consider this as product of the first j terms times the rest. And this product is supposed to be the neutral element, which means the first bunch is the inverse of the second bunch. So product of x sub 0, x sub 1, x sub j minus 1 is the inverse of the product of the rest of x sub k's. So this product is simply inverse of this one. Now, when I give you inverse of, when I tell you that this is inverse of the other one, it doesn't matter if I multiply from this side or the other side, I end up getting the neutral element. So instead of multiplying them like this, now I can put it behind it, and I will end up getting the neutral element anyway. So as I put these guys behind these, I end up getting that this product, x sub j times the next one till x sub p minus 1, and then starting from x sub 0, x sub 1 x sub j minus 1, this product is still the neutral element. So that means what? If I tell you that this p tuple is inside x, then so is this one. I can cyclically change them and still get a point inside x. So again, pictorially, this is what we are doing. I started with x sub 0, x sub 1, x sub 2, and I multiplied them till I reached to x sub p minus 1. And this was my starting point. Now what we are saying is that if I still use the same term, the same xi's, but rotate it j times, and this time my starting point would be x sub j, and then I go multiply them till I reach to x sub j minus 1. So I'm moving cyclically, I'm moving. If I focus on the indices, I'm essentially going mod p. So as I do that, I'm going to get the still identity. As I multiply them, I'm going to get still the neutral element. And therefore, starting with x sub j, I get again another point inside the set x. This means that as I rotate, I'm still inside the set x, and therefore I get an action of the finite cyclic group of order p on the set x. And this action simply says that when I give you the residue class of j mod p, simply rotate the solution that's given by xi's j times, and start from x sub j and then continue. So essentially I'm saying that you need to add the indices by j mod p, and that would be my action. So when I let j, the residue class of j, act on some point, I essentially add the residue class of j to the index, to the indexes. And so when I apply j and then apply I am adding the residue class of I plus the residue class of j to the indexes. And therefore it's the same as letting their summation act, which means it is indeed an action. So star does give me an action of the cyclic group of order p on x. Now notice that this is a cyclic group of order p, it's a prime number. So I can use the previous theorem that we have and deduce that cardinality of x is the same as cardinality of the number of fixed points, is the same as the number of fixed points mod p. Now, remember, cardinality of x is cardinality of g raised to power p minus 1. And because p divides cardinality of g, p divides cardinality of x. So this side is simply 0 mod p. Therefore, this side is a multiple of p. So p divides number of fixed points of z sub p. But what are fixed points of z sub p? Let's think about it. A point x sub 1, x sub 0, x sub 1, dot, x sub p minus 1 is a fixed point under this action, precisely when, for every residue class, as I apply this residue class to this point, I do not move the point. But when I apply this, I'm simply rotating it j times. I'm simply adding j to the indices, so I am getting this point. And still, this is supposed to be the same as old one. That means x sub j should be the same as x sub 0. And the other xi's should be the same after I shift them by j. But this is true for every j. So x sub 0 is supposed to be x sub 1, is supposed to be x sub 2, is supposed to be x sub p minus 1. So all these x sub i's are supposed to be the same things. So this is in the fixed points if all the components are equal. And of course, it's supposed to be a solution of their product to be identity. So this means I'm looking for x, 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 p of them, so that x to the p is the neutral element of the group. All of a sudden, I get to the equation that I was interested in. Now, notice that this set, okay, now, but so far we have proved that this set, the cardinality of this set, should be a multiple of p. Now, we have also a trivial solution. If I pick the neutral element and put it neutral element, this is here, and it satisfies this equation. Therefore, it is a fixed point. So the number of elements of this set of fixed points is at least 1, and it's a multiple of p. So it should have at least p elements. A positive integer that's a multiple of multiple of p is at least p. Positive integer that's more than 1. I mean, a positive integer that's a multiple of p is at least p. So that means we have at least p fixed points of z sub p. P is a prime number, it's not 1. That means we have at least one fixed point, which is not identity, 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 identity. So there exists some x, so that x to the p is the neutral element, but x is not the neutral element. Because x is not the neutral element, its order is not 1. Because x to the p is the neutral element, its order divides p. P is a prime number. The only positive divisors of p are 1 and p. Order of x is a positive divisor of p. It's not 1, so it should be p. So that completes the proof. So we see how we used the action of this simple finite p group, cyclic group of order p, to deduce Cauchy's result that every finite group that has a prime factor p has an element of order p. Let's see another example of this type, and we finish our lectures by this result due to Silu. It's called Silow's first theorem. It's an extension of Cauchy's theorem. So instead of just asking for a subgroup of order p, we are going to ask for a subgroup of order p to the k. So this Silow's first theorem can be also considered as a partial converse for Lagrange's theorem. So G is a finite group, and I tell you that p is a prime number and p to the k divides cardinality of G. Then G has a subgroup of order p to the k. In fact, G has a chain of subgroups, P1 contained in P2, contained in P3, the dot contained in P sub k, And cardinality of p sub I is precisely the prime number p raised to power I. We are going to proceed by induction on K. Of course, the base of induction when K is 1 is essentially Cauchy's theorem. So the base of induction we don't discuss. That's essentially Cauchy's theorem. We are going to focus on the induction step. That means what? That means I'm going to assume that for p to the k, we know this result, and I want to prove it for p to power k plus 1. So assume p to power k plus 1 divides the cardinality of G. For sure, then p to the k also divides it, and therefore by the induction hypothesis, we do have a chain of subgroups p sub 1 contained in p sub 2 till p sub k, and cardinality of p sub I is the prime number p raised to power I. Now I want to go one step further. I want to find a subgroup of order p to the k plus 1 which contains the subgroup capital P sub k. And we are going to achieve this. We are going to find that subgroup by using an action of this top group of order p to the k. Now, what action? I'm going to consider the action of this subgroup on the left cosets of the same subgroup. So I'm looking at the left cosets of p sub k in G and letting p sub k act on it by left multiplication. What do I mean by that? So an element of this group acting on a coset of this by simply multiplying x by this coset representative and then looking at the coset. One can check that it is indeed a group action. Now, because cardinality of p sub k is a power of the prime number p, I can use the result that we proved about fixed points of groups whose order is power of a prime, and deduce that cardinality of this set is the same as cardinality of the cardinality of the fixed points of this action mod p. So modulo p, the number of fixed points, is congruent to the cardinality of G mod out by P sub k. But remember, G mod out by P sub k, by Lagrange's theorem, is simply cardinality of G divided by cardinality of this group, which is P raised to power k. Now, what is the assumption? The assumption is that P raised to power k plus 1 divides cardinality of G. And so P divides cardinality of G divided by P to the k. Still one prime, at least one prime is left in this quotient. So P divides the cardinality of the set of the left cosets. So why did we care about this? Because I care about this congruence relation, and we just said that this side mod P is 0. So the other side mod P should be 0. So that means the number of fixed points of P sub k needs to be a multiple of P. So that's exactly what I have over here. Now let's turn our attention to understanding the set. What can we say about the points that are fixed under P sub k? Let's write it down. A point is fixed. A point here means a coset. A coset is fixed by P sub k if and only if for every element of P sub k, as I let x, as I shift it by left, as I multiply it from left by x, I don't move it. How can that be? That means this coset is supposed to be the same as this one. Okay, how can that be? Two cosets are equal precisely when this guy inverse times this guy belongs to the subgroup. So for every x inside P sub k, G inverse times this, G inverse times this is supposed to be inside P sub k. So for every x inside the subgroup, I have this. Now I put it back here. That means when I conjugate P sub k by G inverse, when I look at G inverse times P sub k times G, I have to be still a subset of P sub k. But notice, these are finite sets, and they have the same cardinality because conjugation is a bijection. In fact, it's an automorphism. So this has the same cardinality as this one. And this is a subset of this one. Therefore, they are equal sets. Remember, that means G belongs to the normalizer. So I can simply multiply both sides by G, and from here I get that P sub kg equals to G P sub k, and that we call to be the normalizer subgroup of P sub k. We prove that this is a subgroup of G. So altogether, we get that this coset is in the fixed points precisely when the coset representative is in the normalizer subgroup. And so the set of fixed points is simply the set of left cosets in the normalizer subgroup. The left cosets of P sub k in the normalizer subgroup. So this cardinality of this is supposed to be a multiple of P. Therefore, cardinality of this is a multiple of P. Now notice, here is the magic. The point is that because of this, because this holds for every G in the normalizer, P sub k is a normal subgroup of this smaller group. And therefore, this quotient is a group itself. Now this is a group and its order is a multiple of P. So it's a group and its order is a multiple of P. Therefore, I can use Cauchy's result again. I can use Cauchy's theorem for this quotient. And by Cauchy's theorem, this quotient has an element of order P. So this has an element of order P. So suppose this coset is of order P. So order of this element is P. Then let P sub k plus 1 to be the cosets that are coming by powers of G. P sub k, G P sub k, G squared P sub k, G to power P minus 1 P sub k, and think about it as a subset of the group G. This subset, of course, contains P sub k, and its cardinality is some of these cardinalities because these are distinct elements of the coset, so they are distinct cosets. And each one has cardinality P to the k. So I have P cosets that are distinct, they are disjoint, and each one has cardinality P to the k. Altogether, we get P to power k plus 1 points. And it's a good exercise for you to show that this is in fact a subgroup. Use the fact that P sub kg equals to Gp sub k to show that this is closed under multiplication and taking inverse. Therefore, it's a subgroup of order P to power k plus 1, and it contains P sub k as a subset. That completes the proof. You see how we used group action and induction process in order to prove Silow's first theorem. Silu proved second and third theorems. They are famous, and those theorems can give us a better understanding of subgroups of the form whose order is a power of a prime. We are not going to discuss Silow's second and third theorem, but I just want to point out that their proof are also based on the fact that cardinality of a set X is congruent to the cardinality of fixed points of action of a group P, or if cardinality of P is a power of the prime number small p. So this is an extremely important result which has many implications. Okay, let me stop at this point, and I hope that you enjoyed group theory. And next time that you face a new problem, you ask yourself, can I use symmetries to solve this problem?